Hello, Dr. Tullis here, just sipping some tea out of my favorite mug. We are looking at Chapter 10, and this is about bonding and properties of solids and liquids. We'll be investigating electronegativity, bond polarity, drawing Lewis structures to get an idea of the shape of different compounds, and looking at compounds that are polar and nonpolar. Let's get started. The career focus for Chapter 10 is a histologist. A histologist studies the microscopic makeup of tissues, cells, and body fluids. They determine blood type and the concentration of substances in the blood, and they also prepare tissue samples that are analyzed to look for abnormalities. Section 1 is about Lewis structures for molecules and polyatomic ions. You'll be able to draw the Lewis structures for molecular compounds and polyatomic ions with single and multiple bonds. A Lewis structure is a convenient way to represent the valence electrons, the outermost electrons, which are shown as dots placed on the side, the top, or bottom of the symbol of the element. Any of the following would be an acceptable Lewis symbol for magnesium, which has 2 valence electrons. You pretend that there's a box around the element symbol. So for example, if we had magnesium, you do 1 dot per side before you double up. So if you want to do a top and a bottom, that's fine. Or like they showed us up here, they did a top and a bottom, they did a top and a side, a top and a left, the left and a right side, a bottom and a right, a left and a bottom. Doesn't matter, as long as you don't put them on the same side. Here's some Lewis symbols for certain elements in periods 1 to 4. So everybody in group 1 has 1 valence electron: hydrogen, lithium, sodium, potassium. By just writing the symbol stands for the nucleus, everything in the nucleus, and all of the inner electrons. That's why K and Na both have 1 dot. Yes, potassium has more electrons than sodium does, but they're all inside electrons. They're not the valence electrons. The outermost electron, everybody in group 1 has 1 outermost electron. Everybody in group 2 has 2. Everybody in group 3 has 3 outermost electrons. And if we were to look at aluminum, for example, they have it with a side, a top, and a side, but it could be like this as well. The dots do not have to be just like these guys. We just can't double them up. Carbon, silicon, germanium, these guys have 4. There really isn't another way to draw 4 because you have to have 1 on each side. Then we get to 5, nitrogen. They have the 2 on the top, but you could also do it like this: 1, 2, 3, 4, double up on the right side. You could double up on the bottom, on the left. Doesn't matter. Oxygen, sulfur, and selenium, they have 6 valence electrons, so they have 2 sides where electrons are paired up. For the fluorine, chlorine, bromine, they have 7. Here they have 3 sides that are doubled up to give us 2, 4, 6, and then plus 1 is 7. And neon, argon, krypton are full at 8. Now helium is the only time where I would put 2 electrons on the same side. We want to show that helium doesn't have any lone electrons that want to bond. Helium is full. An ionic compound forms when valence electrons from metal are transferred to a nonmetal. For example, the transfer of 1 valence electron from sodium to chlorine gives octets to both. The loss of an electron by sodium produces a sodium ion. So sodium wants to lose 1 electron. And when it does that, it then becomes like the noble gas that's right before it. Look at your periodic table and put your finger on Na, sodium, atomic number 11. Here's sodium. Sodium has 11 protons, 11 electrons, and it has that 1 outermost electron. If it loses 1, it goes from having 1 electron in the 3rd energy level to being like neon and having a full 2nd energy level that has 1, 2, 3, 4, 5, 6, 7, 8. It has an octet like neon if it loses the 1 electron. Now let's look at chlorine. Chlorine is right here. Chlorine is only 1 electron away from being like argon and having a full 3rd energy level and having an octet. So if chlorine gains 1 electron, it becomes a -1 ion. That's why if sodium loses 1, it becomes a +1 ion. Chlorine is actually like, ooh, I'll take that one electron. Sure, I got a spot for it right there. Now I have an octet and I have a -1 charge. Sodium has an octet, and even though we don't have 8 electrons around sodium, we show that it has a +1 charge. It might look like there's no electrons, but we need to be able to recognize that it gave one away, so it has the same electron configuration as the noble gas before it, which is a full octet. There are some elements that exist as diatomic molecules. That means that they do not like to be just by themselves. They're very unstable. They like to be in pairs with another atom just like itself. For example, hydrogen always likes to be found in nature as H2 when it's by itself. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine. See how it makes a number 7? There are 7 elements that like to exist paired up with itself. And notice that this makes the number 7, and then add hydrogen to it. You can also remember who likes to be diatomic by knowing the phrase Brinkelhoff. I know it sounds silly, but bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine are the 7 elements that exist in diatomic molecules. Again, that's when they're by themselves. So if I said hydrogen plus oxygen can yield water, we don't just say H plus O to give me H2O. Hydrogen by itself is H2, oxygen by itself is O2. Now in a compound, that's not the case. We can have different numbers of hydrogens and oxygens when it's in a compound, but when they're by themselves, they are diatomic. So knowing that, let's look at the Lewis structure for the hydrogen molecule. The simplest molecule is hydrogen, H2. When 2 hydrogen atoms are far apart, there is no attraction between them. As those hydrogen atoms move closer, though, the positive charge of each nucleus attracts the electron of the other atom. This attraction, which is greater than the repulsion between those outermost electrons, because we know that electrons and electrons want to repel each other, but the attraction between one nucleus and the other electron is greater. So it pulls hydrogen atoms closer until they share a pair of electrons. We know hydrogen is in the first group, so it has 1 outermost electron. So another hydrogen has 1 outermost electron. These two are going to share, or we can also write it like this. So it looks like they have that pair right there, which also looks similar to how helium looks. If I were to look at the periodic table and see helium right up here in the top right, if I drew the Lewis structure for helium, it would look like this. It's full and has 2 outermost electrons. Well, guess what? So does hydrogen, H2. When they share those 2 electrons, they then have 2 and they're full. This is called a covalent bond. We have shared electrons, which give us a stable electron configuration of helium to each of those hydrogen atoms. If I covered up one hydrogen, let's say I covered this up, this hydrogen on the left has the electron configuration of helium. And if I did the other way and covered up the left hydrogen, notice that this right hydrogen has the electron configuration of helium. So when the H atoms form H2, they are more stable than 2 individual hydrogen atoms. This shows exactly what I was doing in a much more organized fashion. We can see our hydrogen with 1 dot, hydrogen with 1 dot. They're far apart, there's no attraction. But as the distance between my nuclei decreases, so they get closer and closer, those attractions pull atoms closer, and then we end up with a hydrogen molecule. We represent that molecule with a Lewis structure. The valence electrons of the atoms are arranged to give octets, or in the case of helium, it has 2, but we still call it a full outermost shell. Hydrogen, which has 2 electrons, does not get an octet. The shared electrons, or bonding pairs, are shown as 2 dots, or a single line between atoms. So we can show that even though we started off with those 2 dots, 2 electrons, the shared electrons, or bonding pairs, we can show like this as well. A single line showing that bond. The non-bonding pairs of electrons, or lone pairs, are just placed on the outside. Let's look at fluorine. F2 consists of 2 fluorine atoms. The fluorine atoms are in group 7A with 7 valence electrons. In the Lewis structure for the F2 molecule, each fluorine atom achieves an octet by sharing its unpaired valence electron. Let's see what that looks like. Fluorine F has 7. 1, 2, 3, 4, 5, 6, 7. Fluorine wants 1 more. Well, look at this fluorine. It has one that's not paired up. It would love to share that one. If I have another fluorine, 1, 2, 3, 4, 5, 6, 7. If these two share their only electron that is not paired up, again, if I pretended like I'm only looking at this right fluorine, this right fluorine now has 2, 4, 6, 8. It has a full outer shell by sharing that other electron. Let's look at the other fluorine. Scribble out the right fluorine, and now my left fluorine also has 8, a full octet. So here I can see what I was just drawing, my bonded pair, which is a shared pair of electrons. We can also replace that shared dot with a line showing that covalent bond. We can also show it two other ways, this ball and stick model and a space filling model. Electron dot formulas show the sequence of bonded atoms in a molecule or polyatomic ion. It shows the bonding pairs of electrons that are shared between atoms, the non-bonding or unshared lone pairs of electrons, and the central atom that's bonded to other atoms. The number of electrons that a nonmetal atom shares and the number of covalent bonds it forms are usually equal to the number of electrons it needs to achieve a stable electron configuration. For example, if I looked at boron, and we found boron on my periodic table, boron is in group 1, 2, 3A in my representative elements. Boron has 3 outermost electrons. Boron would love to have 3 bonds. Carbon is my 4th. 1, 2, 3, 4. Carbon has 4 outermost electrons. Carbon would love 4 bonds. Now then we go to nitrogen. And you might think, well, 3, 4, nitrogen wants 5 bonds. But let's draw nitrogen. Nitrogen has 5 outermost electrons. 1, 2, 3, 4, 5 outermost electrons. Now these guys don't want to form a bond. But this one does, that one does, and that one does. So nitrogen would love 3 bonds. And oxygen, we know oxygen has 6 outermost electrons. Notice that 2 sides are doubled up. Oxygen would love to form a bond here and here. So oxygen would like 2 bonds. And the fluorine, chlorine that have 7 outermost electrons, they would like 1 bond.